Look at the formation of this curve. This curve is known as the Koch snowflake curve. In fact, it is a fractal curve. Recall that a fractal is an object or quantity that displays self-similarity. And the Koch snowflake is one of the simplest and most famous fractal curves. Observe that the Koch snowflake curve comprises infinitely many equilateral triangles. So what will be the area of the curve? The curve looks infinite, but it has a finite area. For how can an infinite area be drawn on a finite space? Note that the area inside the Koch snowflake can be described as the union of infinitely many equilateral triangles. Notice that each side of the green triangle is exactly 1/3 times the length of a side of the large blue triangle. Therefore, each green triangle has an area of exactly 1/9 times the area of the blue triangle. There are 3 green triangles in the curve. Likewise, each yellow triangle has 1/9 times the area of the green triangle, and so on to infinite terms. There are 12 yellow and 48 red triangles in the curve. Now, if the blue triangle is taken to represent a unit area, then the total area of the snowflake curve is given by the series shown. In the obtained infinite series, the first term represents the area of the blue triangle, the second term corresponds to the total area of the 3 green triangles, the third term gives the total area of the 12 yellow triangles, and so on. In order to find the pattern in the terms of the series, exclude the first term in the series and then observe that the remaining terms in the series form a geometric series with infinite terms and a common ratio equal to 4/9. The sum of this infinite geometric series, when added to 1, gives a finite area. Let's explore how the infinite geometric series sum up to a finite number. Now we have an infinite geometric series with the common ratio 4/9 and the first term 1/3. Label this series 1. Remember that the formula to evaluate the sum of n terms of a GP is given as shown. As r is less than 1, we use the formula corresponding to the r less than 1. From series 1, substitute the respective values of a, r and n in the formula. Label the obtained equation 2. Note that the value of the higher powers of 4/9 decreases continuously as shown. As a result, when the power n approaches a very large number, the value of 4/9 to the power of n will be nearly equal to 0. So we can conclude that 4/9 to the power n, when n approaches infinity, is equal to 0. Hence, equation 2 is reduced to equation 3, which on simplifying gives the sum of the infinite GP series as equal to 3/5 as shown. Now let's go back to the area of the Koch snowflake curve. Now substitute the sum of infinite GP series from equation 4 to get the area of curve as equal to 8/5. Let's now generalize to get the sum of infinite terms in GP. Consider an infinite geometric series as shown. Here, the first term is a and the common ratio is r. Let's denote the sum of infinite terms of GP as S, as shown in equation 1. We know that the sum to n terms of the geometric series is as shown. Let's consider the case when r is less than 1. As we have seen, raising a number smaller than 1 to higher powers makes the number progressively smaller. So as n becomes large, r raised to power n becomes nearly 0. Hence, the sum to n terms will reduce to a finite number. Secondly, when the common ratio r is more than 1, then r raised to power n will become larger and larger, making the sum infinite. Therefore, from our observation, we can conclude that for the common ratio r less than 1, we get the finite sum of infinite terms of GP. However, if the common ratio r is greater than 1, then we get an infinite sum for infinite terms in the GP. Since the sum of infinite terms of a GP is infinite for r greater than 1 and finite for r less than 1, so the common ratio r can be negative as well. We can define the sum of infinite terms of GP in an interval with r greater than -1 and r less than 1, or for r ranging from -1 to 1 as shown. Let's find the sum of the given infinite geometric series. In the given series, the first term a is equal to 3 over 10 and the common ratio r is equal to 1 over 10. Now, substitute the values of a and r in the formula to calculate sum of infinite terms in geometric series. Hence, we get the finite sum of the infinite geometric progression. Now find the sum to infinity of the given infinite GP. In the given GP, the first term is -3 over 4 and the common ratio is -1 over 4. Since the common ratio lies between -1 and 1, by using the sum to infinity of the GP, we get the sum as -3 over 5. Did you know that the discovery that the sum of an infinite GP is finite has resolved the famous motion paradox proposed by Greek philosopher Zeno? According to Zeno's paradox, motion is an illusion. Zeno proposed that if a person is 1 foot away from the wall, then before he gets there, he must get halfway there. Before he can get halfway there, he must travel half of the remaining distance. That is, a quarter of the total distance. Similarly, before traveling a quarter of the total distance, one must travel 1/8 of the total distance and so on. As a result, one will take an infinite number of steps and by this logic, one can never reach the wall. This is a paradox because although it seems to be true, clearly it is not. One can get there. Note that the distances covered to reach a wall form an infinite GP with the first term 1 and the common ratio 1 over 2 as shown. Hence, the paradox is resolved by using the principle of the sum of infinite terms in a GP. Therefore, covering the finite distance in an infinite number of steps, one can reach a wall.